Hi everyone. In this video, we are going to learn Euler's theorem. One of the most important theorems in number theory and cryptography. I will explain with simple examples and real life meaning. What is Euler's theorem? Euler's theorem tells us how powers behave when the numbers are coprime. It is general version of the Fermat's little theorem. In this theorem, if A and N are coprime, then we are already discussing about GCD of A comma N equal to 1. In this case, then A raised to phi of N, that is congruent of 1 mod N. Here A is act an integer, N is the modulus, that is coprime means GCD of A comma N equal to 1. In this equation, we are using phi of N. That is phi of N can be represented as Euler's torsion function. That is, the Euler torsion function means the number of positive integer that is less than N that are coprime with N. Congruent of 1 mod N means that remainder become 1. That means if not coprime, the theorem cannot be applied. If a number A and N don't share any common factor except 1, that means the remainder is always 1. For example, first we have to understand the phi of N. Here, the N is 10. The numbers less than 10 means 1, 2, 3, 4, 5, 6, 7, 8, 9. Then coprime with 10. That means, what do you mean by the coprime? We are already discussing about the coprime. Coprime means that is relatively prime means. That means two numbers have no common factors except 1. In other words, GCD of A comma B equal to 1. This means there the greatest common divisor is 1. Here we are using the number become 10. So 10 equal to the factor of the 10 become 1, 2, 5, 10. So in this case, these numbers are divisible by 2 and 5. Here, which number is not divisible, that numbers can be tracked out. In this example, the number is less than 10 means 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 1 is not divisible by 2 or 5 and 2 is divisible and 3 is not divisible. Again, 7 is not divisible, 9 is all divisible. So, here the coprime with 10 become 1, 3, 7, 9. That means it is not divisible by 2 or 5. So, phi of 10 equal to 4. Then, why do we use for the Euler's theorem? Because it will be used for to find the modular inverse when the modulus is not prime, that we have applied the inverse formula. Then in this equation we can divide both sides become A. So the expression become A raised to minus 1 congruent of A raised to phi of N minus 1 mod n. Here, if A and n are coprime, that means inverse existing. For example, find the inverse of 5 and mod 30. Here, first we have to apply the equation. In this equation, A become 5 and n equal to 13. 13 is a prime, so we can use the Fermat's theorem. So 5 of 13, 5 of 30 minus 1, that is equal to 12 minus 1. We can first we have to find the 5 of 13. How to calculate the 5 of 13? By using previous step. So if here the n value become 13, so we calculate the power of the factor of the 13. Factor of the 13 become 113. So n is less than 13. N is less than 13. We are using 1, 2 up to 12. So these numbers are not divisible by 13. So here the total number of 5 of 13 equal to, that is coprime with the 13 equal to 12. 12 numbers is tracking. So 5 of 13 equal to 12. 12 minus 1 equal to 11. To apply the equation, A equal to 5 raised to minus 1, that is congruent to 5 raised to 5 of 30 minus 1. 5 of 30 minus 1, 5 raised to 11, that is mod 13. Then here the 5 raised to 11 will be act as power term. So we apply the Fermat's little theorem. Then step by step power reduction method. First we have to apply the first square method, that is 5 square equal to 25. Then 25 is divisible by 13. By applying the division formula, the remainder become 12. But in our case, we have to, the remainder is equal to 1. So in this case the remainder is not equal to 1. So again we applied the another square. So previously we have to apply the 5 square, that means the 5 square the whole square, then 5 square the previously used in the remainder become 12. So that remainder is copied into the next square method, that is 5 square is replaced in 12 and 12 whole square, that is equal to 144. Then now reduce the 144 mod 13. In this case the remainder is 1. So in our remainder equal to 1, we stop our execution. Then 5 raised to 4 is congruent to 1 mod 13. Now make 11 as a combination. So the decomposition of the 11 equal to 8 plus 2 plus 1. In case of the power term, 5 raised to 11 equal to 5 raised to 8 into 5 square into 5 raised to 1. So 5 raised to 8 can be decomposed into 5 raised to 4 the whole square into 5 square into 5 raised to 1. 5 raised to 4 the whole square, the remainder become 1. So 1 square dot 12, 5 square equal to, in previously 5 square equal to 12. So remainder 12, 12 dot 5 raised to 1 equal to 5. So then multiplied in 1 into 12 into 5. So answer become 60. Then 5 raised to 11 is replaced in 60 mod 13. So 60 mod 13, the remainder become 8. The 5 raised to 11, that is congruent to 8 mod 13. The inverse of the 5 raised to inverse, that is congruent to 8. That is our modular inverse equal to 8. Students often get confused about when to use Fermat's theorem and when to use the Euler's theorem. So let's take the same problem and solve it using the both methods. In our previous video, we are explained the Fermat's little theorem. In this video, we are to focusing on the Euler's theorem. That both case are the value become 8. So both methods are give the same answer. The Fermat is actually a special case of the Euler. So in this case, the prime modulus is by using the use Fermat's, and composite modulus is by using the Euler's theorem. That is the mainly tip for the difference between the Euler's and Fermat's theorem. So now you clearly know the difference between Fermat's little theorem and Euler's theorem using the same examples. In case of real-time application, we are using the Euler theorem is used in RSA encryption, online banking, UPI and digital payments, HTTP security, key generation. That means whenever secure data is sent, Euler's theorem works silently in background. That's all for today. We learn Euler's theorem, its meaning, examples, modular inverse formula and real-life application, and how it compares with the Fermat's theorem. Thank you for watching. Hi everyone. In this part, we are going to learn method C for finding the modular inverse using very famous theorem that is called Fermat's little theorem. This method is super easy when the modulus is prime. What is Fermat's little theorem? The theorem says that this method only when the modulus is a prime number. The theorem says a raised to p minus 1, that is congruent 1 mod p. If p is prime and a is not a divisible, p rearrange to get the inverse. If we divide both sides by a, the equation become a raised to p minus 1 divided by a, that is congruent to 1 by a mod p. Rewrite the equation a raised to p minus 2, that is congruent a raised to minus 1 mod p. That means inverse of a mod p, that is equivalent to a raised to p minus 2 mod p. So the formula for the modular inverse is a raised to minus 1, that is congruent to a raised to p minus 2 mod p. It is used only when p is prime. Now move on the example. Find inverse of 5 mod 13. Here a will be act as 5 and p will be act as 13. 13 is prime. Using this formula, a raised to p minus 2, that is congruent to a raised to minus 1 mod p. Apply these values. A will be act as 5. 5 raised to p is 13. 13 minus 2, that is congruent to 5 raised to minus 1 mod 30. So we need to rearrange in our equation 5 raised to minus 1, that is equal to 5 raised to 11 mod 30. So we need to compute 5 raised to 11 mod 13. Then going to the another step, that is used to repeated squaring method. It is a fast method. In this case, we compute the powers. First one is the first square. Here 5 square equal to 25, that is congruent to 12 mod 30. Then 5 square equal to 25, we apply divide 25 by 13. Then 25 equal to, by using the division formula, 25 equal to 13 into 1 plus 12. In this case, the remainder become 12. So 5 square is congruent to 12 mod 13. Then move on the another square, that is the 5 raised to 4. 5 square the whole square, that is the 5 raised to 4. In previous step we found that 5 square equal to 12. Therefore 5 squares, to substitute the 5 square value, that is equal to 12 the whole square. Then value become 144. Now reduce 144 mod 13. That is 144 is divided by 13. Then the remainder become 1. So 5 raised to 4 is congruent to 1 mod 13. In this case, the grade found method. Then 5 raised to 1 equal to 1. That is 5 raised to 1, that is congruent to 1. Then going to the another step, that is the break the exponent 11. That means break the power of the 11. In this case, we want to 11 in terms of by using the decomposition. Here, the decomposition means breaking a number into the smaller convenient parts. Suppose we have to using two methods can be performed in decomposition. First method is break using simple addition. Normally 11 can be 8 plus 2 plus 1, because 8 plus 2 equal to 10, 10 plus 1 equal to 11. Here we just choose convenient parts that adds up to the 11. Then another method for the decomposition, that is break using power of 2. That means find the powers of 2 less than or equal to 11. That is power of 2 equal to 1, 2, 4, 8, 16. That is less than 11. In this case, we stop the at 8. Then now subtract step by step. First we have to subtract 11 minus 8, that is equal to 3. Again choose powers of 2 less than 3. In this series, we stop the 4. That is, we take the value 2. That is 3 minus 2 equal to 1. Again remaining is 1. That is, take the 1. So, in our decomposition, 11 equal to 8 plus 2 plus 1. Then move on the Fermat's little theorem. In this case, we have found the three equation, that is 5 raised to 4 congruent to 1 and 5 square congruent to 12, 5 raised to 1 congruent to 5. Now express 11 as decomposition, 11 equal to 8 plus 2 plus 1. So, 5 raised to 11 will be act as 5 raised to 8 into 5 raised to 2 into 5 raised to 1. Now evaluate each part. 5 raised to 8 equal to 5 raised to 4 the whole square. In this case 5 raised to 4 will be act as 1. So that is congruent to 1 square equal to 1. Then 5 square, that is congruent to 12. 5 raised to 1 is congruent to 5. Then multiply in our 5 raised to 11 equation. 5 raised to 11 equal to 5 raised to 11 congruent 1 into 12 into 5. The value become 16. Now reduce mod 13. Then 16 equal to, by using the division formula, 13 into 4 plus 8. The remainder become 8. In this case, 5 raised to 11, that is congruent to 8 mod 3. So the inverse, the 5 raised to minus 1, that is congruent to 8 mod 13. Here in our equation 5 raised to 11 mod 13, in 5 raised to 11 value become 8. So our equation become 5 raised to 5 raised to minus 1 congruent 8 mod 13. Find the verification process to check 5 into 8. That means 5 raised to minus 1 to represented as 1 by 5. That is equal to 8 mod 13. So to apply 5 into 8, that is equal to 14. 14 is divisible by 13. So in this case 14 is divisible by 13. That is remainder become 1. So 14 is congruent to 1 mod 13. So the inverse of 5 mod 13 is 8. So our equation will be correct. That's all for method C. We learn how to find modular inverse using Fermat's little theorem, which works beautifully when the modulus is prime. Where do we use Fermat's theorem and modular inverse in real life? By using the digital signature like the online transaction, then using encrypted communication, for example our WhatsApp, Google Pay, banking apps, etc. Then real life another example is the public key cryptography by using the RSA algorithm. In this system you need to compute inverses of very large numbers and modulus is often a very large prime. Fermat's little theorem makes inverse calculation much faster. So every time you send a money online, logging securely or use OTP, this method helps to secure your data. And that's all for today. We learned how to compute modular inverses using Fermat little theorem with a simple example and even a real life connection. In the next video, we will explore Euler's theorem, which is the general version of Fermat's method when the modulus is not prime. Thank you for watching.